Hi, I'm Mike Stanzik and this is Digital Electronics Classroom. In this video we're going to look at modulus counting. Now, modulus counting is a count in which we don't go through all the states that are possible in our flip-flop system. So for instance, if we had 4 flip-flops in our counter, that means that we would have 16 possible states, 0 through 15 or F. But if we didn't want to count between 0 and 15, we have to do something to our circuit so that we can count through a different range. And so one range that we might want to count from to is maybe 1 through 5. Maybe we start at 1 and count up to 5. And in that case, we would have a mod 5 counter because our states would be 1, 2, 3, 4, 5. Now, it's not mod 5 because the last number is 5, it's mod 5 because there's 5 states. So it would still be a mod 5 counter if we were counting from 2 to 6, or if we were counting from 3 to 7, or 4 to 8, and so on. So the number of states that you count through is the modulus number. And so today, in our example, we're going to count from the number 3 to the number 9. So what modulus would that be? 3, 4, 5, 6, 7, 8, 9. So that's going to be a mod 7 counter. Okay, so we're going to look at how we set this up, how we make it start at the number we want it to, how we make it end at the number that we want it to in this video. So let's get started. Oops, I'm on the wrong page to start. This is the one I want. Great. Okay, so modulus counting. Mod counting. Okay, all right, so there are a couple things that we want to just remember from what I introduced here, is that mod number is equal to the number of states. And so 2 to 6, which is 2, 3, 4, 5, 6, is a mod 5 counter. Okay, so that's the one thing that we want to know. Basically, there's 2 things we have to do. We have to set the number that we start at, and we have to be able to detect the stop number. So those are the 2 things that we want to be able to do, okay? So in our asynchronous or direct inputs video, we talked about how we set a set of flip-flops to a number. And, so that's something that we sort of know how to do. So in the example I'm going to do here before we go to, you know what, let's do the 3 to 9 here as well. So I'm just going to kind of draw out some flip-flops. And they keep on getting wider. And so remember that this is the least significant bit. That's something that we really want to make sure that we're aware of when we arrange our flip-flops like this for a counter, because when we set it, we want to set it to the right number. And so we're up counting. In this case, we're going to up count from 3 to 9. And so the 3 binary number looks like this, 0, 0, 1, 1. And the 9 binary number looks like this, 1, 0, 0, 1. And so we want to set it to 0, 0, 1, 1. That's when we're going to start counting. And so remember that we have the top set and the bottom is reset for each of these. And so we want to set this such that it reads 0, actually let's do this, 0, 0, and then 1, and then 1, right? So that's what we want to do. So we're going to connect to those spots on the set and reset. So there's a 1, connect here, that's also a 1, connect here, that's a 0, and then connect here, that's a 0. And so this is where, you know, we want to activate when we reach the stop, right? So our top of our count, we want to activate that. And so then it will activate those sets and resets appropriately, and we get 0, 0, 1, 1. Now, the other thing that we want to do is make sure that the opposing set or reset does not activate. So we're going to take all of these guys and then connect them together, and then we're going to force them to be low. So the reason why I'm going to force these to be low, so we can put that as a 0 or as a ground, okay, is because these are active high inputs. There's no bubble on these inputs, so they're active high. And so this signal here that comes in when we activate it needs to be a high signal. And so we want to have something that goes to 1, and that's activating. And then this one we want to keep it a low signal so that it does not activate. Okay. So that's what we're doing when we're doing our set. So this here is set, right? What about the reset part then? So let's see. Might have to draw this a little smaller here. Okay, so for a reset, we need to detect when we reach past the number 9. And you know, actually I'm going to do this on the other screen, so let's go to the other screen here. So I have here a truth table and a Carnot map. And so let me kind of highlight some things. First off, this is the number 3. And then the number 9 is right here. Okay. So we want to include all of these numbers in our count. And so this is the direct input. This is where we are going to trigger our set and resets, right? So while we're inside the count that we want to be in, this should not be activated. And as we're counting up in number, we want to keep it inactive all the way through number 9. But then at number 10, so right when it turns into 10, we want to immediately activate it, and so we'll go back to the number 3, okay? And so let's assume that we're not going to have any other states, and we're just going to be counting up through these states that we start at 3, and we're going to count up through these states, and then we're going to reach the number 10, and then it's going to go back to the number 3. In that case, we have don't care conditions for all the other states. Now, if you want to design for instability or for a start state that is not 3 through 9, then you could make these all 1s, and it would be a little bit more complex combinational logic, but that will handle any sort of accidental movement out of the state that we want it to and reset the counter at that point. Okay, so let's build this truth table then. We got x, 0, 0, 0, 0, 0. I'm really interested in where that 1 is. And so then we got skip, we got and yeah, I'm really interested where that 1 is. So 0, 0, 0, 1, and then x, like that. Okay, and so this is A3, A2, and then this is A1, A0. And so where can we box this 1? We see we can box that 1 right there. And so when are we going to flip? And so I can see that this is A3 and A1, A0. And so this is essentially the 1s in the number 9. And so we don't have to put A2 in there because this particular combination will never happen with an A2 in it, because the A2 only shows up after that point once we have a 1 in A3. And so this is sufficient. And so we've kind of reduced the combinational logic that we might need to use by doing this Carnot map and truth table to do that. Okay. So let's go ahead and look at how we would create that. So remember, we have this input right here. I'll just make it as a circle. This is going to be where we activate the reset, activate the start number, right? But then we have all our Q's and Q bars over here on all of our digits, okay? And then this is A0, A1, A2, and A3. So we want to say, okay, when does that active state, when should it occur? And it should occur here. So when we have A3 and A1 and A0. So in this case, we don't need any inversion, so we're just going to pull out from the Q side. And we're going to use an AND gate. And so if I need A3, I need A1, and I need A0. And so I'll take the output of that AND gate, and then I'll connect it to that set circuit that we had on the previous page. And so I just wanted to break this up into two parts so it didn't look too complex. Okay. Notice that we don't need A2 at all, so we don't need to connect that to anything, so we just let it be, and that's how we do it. What if we were counting to a different number, and instead of having it be A3, A1, A0, it was A3, A1 bar, A0? How would we handle this? Well, then we would connect A1 to Q bar instead of to Q. And so that would be A1 bar entering into our AND gate. So that would be the only difference there, okay? What if our sets and resets were active low? Well, this is going to be an active high, so it's going to go through a transition like that. And so once it goes to active high, that's when we want it to set and reset. But if they're active low, then we have to do one more thing. We have to, instead of using an AND gate here, we would use a NAND gate. And that NAND gate would provide an inversion there, which would make the signal go active low. It would go low. Okay, so those are two modifications that you might make depending on what your circuit looks like. All right, great. Let's go ahead and simulate our example here. All right, so I'm going to take a minute to kind of build this up. So we're going to use D flip-flops. Oh, okay. Good enough, I think. And so first off, they're a counter, so let's make them counters. So we have to go ahead and connect them into toggle mode. Okay. We want this to be an up count, and I might need to spread them out a little bit more. We'll see. Here, let's see, will this go with it? Yeah. Okay, I think that'll be good. 1, 2, let's do that. Let's do this one. Okay. So this is going to be up count, so that means we have to connect to Q bar. So connect to Q bar. All right, we'll put a clock input as a digital constant. And so first, the set circuit is going to be connecting, making this into a 3. And so we said we needed, I'm just going to use this for the time being to help build that set circuit. And so we're going to have these both be set to 1. and then these two be reset to 0. Okay. We also need to have the other ones tied to 0, so I'm going to use a second digital constant to do that, and I'm going to put it, I'll put it on this side too. Alright, so then we need to reset, make sure that's going to be a 0, and make sure these sets are also going to be zeros. Maybe I'll do this. Okay, that looks good. So I can't turn this to 0 until we start simulating, but then as soon as we start simulating, I'll turn that to 0 to make sure that those inputs are not activated. So you can see it starts to look a little bit complex. So that's why I drew those two circuits beforehand. So hopefully you can still kind of see what's going on. We needed a 3-input AND gate for our detection. And so let's go ahead and put that there. And we said we wanted to detect on A3, A1, and A0. So we need A3, A1, and A0. Okay, and now this is actually connected back to this circuit right here. And this is not connected there. Okay, so that's what we wanted. I will enter another one of these for our clock. All right, so that's our clock. This one's set to 0. Last thing, we want to see what's going on. And so I'll put a hex display in. Nope, not that one. This one. Okay, so we can see our count. And so remember, this is 3, 2, 1, 0. And so D is our highest significance, so we're going to connect that to the Q here. And then we'll connect this one to Q for 2, and we'll connect B to Q for 1, and we'll connect A to Q for 0. Okay, that looks good. Hey, now we're doing some digital electronics. This looks like a pretty serious circuit. It might seem intimidating, but notice that we did one thing at a time, and once we got that one thing done, we moved on to the next thing. And so hopefully we've gotten it all correct. But you know what? You might not. And that's part of doing engineering, is that you're going to make mistakes, and then you got to go in and correct them, and that's totally fine. Okay. So let's go ahead and see if we got this connected up properly. Oh, yeah, okay. So I'm gonna start to, see, we started outside of the range. So now we're at 3. So that's what I was talking about before. So we were in an unstable state, but now we got to a stable state. We're at 3. So let's start to count out from there. We got 4, 5, 6, 7, 8, 9, and now this should switch back to 3, and it doesn't, so we have something not quite right here. Oh wait, I think I connected it wrong. We needed A3, A2, let's see, not A3, A3, A2 and A1 for 10, 8, 9, 10. Wait, let me go back to the other sheet, because I think I might have done something wrong over here. What did we say we need? A3, A1, A0. That's what we did. So A3, A1, A0, and because I did this wrong. Because I went up to here. See what I'm saying, make mistakes, right? This is actually 10, not 9. So we needed not this one to be a 1, but this to be a 1. So let me go ahead and correct that here. And I'm just going to kind of scribble over. So it's 0, 0, 0, 1, 1, but it should be 0, 0, 1, 1x. Sorry about that. And so that actually stops right there. So, so 0, 0 should be a 1 here and an X here. Okay, so that actually changes things for us. That makes it an easier box. It's a bigger box. What does this box say? This box says A3, A1. So just A3 and A1 should allow us to make that count appropriate. Now I'm not sure, but let's give it a try. So we made a correction. Let's see if that works. This is great because you guys are seeing the engineering process in action here. So A3, A1 instead. So let's get rid of this. Oh, I can't because it's simulating. All right, there we go. Get rid of that. So we just need a 2 input AND gate. And we need A3, which is down here. And we need A1, which is this guy right here. And then that connects to this circuit up here. Ooh, okay, let's try it. All right, so it starts not in the sequence, but now we're at 3, 4, 5, 6, 7, 8, 9. Now this should go to 3. Hey, 3, 4, 5, 6, 7, 8, 9, and 3. Yes! Okay, so a little bobble there, but we corrected it and totally fine. That's how it works. So here you see the operation of a 3 to 9 mod 7 up counter, and with D flip-flops and active high sets and resets. And yeah, so again, if you have any questions, post them in the comments or send me an email or whatnot. I'm Mike Stanzik at Digital Electronics Classroom, and have a wonderful day.